Hello and welcome to Chemistry for the Interdisciplinary Sciences. This is lecture 9. Today what we're talking about is energetic change in reactions. So let's have a glance at the learning outcomes. Today what I'd like us to be able to do is to describe the energy change of a reaction. So that is where the atoms are rearranging, swapping partners, or ions are rearranging and swapping partners, and there is some reason for it to do that, and that tends to be energetic change. We're going to be able to calculate the theoretical enthalpy change of a reaction, and also we'll look at how we actually measure this in the real world, because we know that theoretical values are not always the same as real world values. So to start us off, we'll just define a couple of terms that I'm sure you're aware of, but they're just worth keeping in mind, and that is exo, meaning on the outside, and endo, meaning on the inside. So if I had a way cooler job, I could wear an exoskeleton, but alas, I have to live with the endoskeleton that I have. So in this lecture, what we're going to look at is this idea of giving out energy, and we'll call that an exothermic reaction, and taking in energy, which we'll call an endothermic reaction. The experience of those reactions, though, is that one of them gets hot and one of them gets cold. So the quintessential exothermic reaction that we've seen time and time again is something like this. And we're just going to watch the slow-mo guys for a second because they film good fire. So let's have a look. So here what we can see is technically a reaction. It's a bit of petrol, I think, mixing with the air. And in that reaction, we see light is given off, heat is given off, and look how beautiful it is. It's only when the mixture of petrol and air is correct that we see any form of reaction happening at all. And look how beautiful it is. Now, why? Why is this happening? Why are some substances super flammable, and yet something like a beaker of water isn't going to set on fire at all? Well, the answer has to do with the bonds that are involved in that compound itself. So let's have a quick glance at some processes. I want you to have a quick think about it and think, does this process give out energy, require the removal of energy from the reaction vessel or the system or whatever? Or does it give out energy? Does it have to take it all out and allow that system to reduce in energy? So just have a quick think about each one and we'll talk about them as we go. So let's just start with this. Making ice cubes. So to make an ice cube, I've got to put that in the freezer. And the freezer's job is essentially to remove energy from the cabinet, which I'm sure is not the real word, from the cabinet out into the atmosphere. So all a fridge and a freezer is doing is just moving the energy out. In so doing, we remove enough energy from the water molecules to make them stop moving around. You remember we mentioned that the more heat they have, the more they move around. Well, when we cool them down in a freezer, they're going to stop moving for long enough to start making those links and becoming a solid in there. So this is an exothermic reaction. Yes, it has to give out heat in order to make that change. Let's look at the next one. The evaporation of water. So again, have a think about it and do pause if you need to. So the evaporation of water requires that there is some energy provided by, for instance, the sun. If we put out our wet clothes, we use the sun to dry them. If we might need to use a fan or something like that. But the evaporation of water requires us to input energy. So if energy is going into the water, then that means that this is an endothermic change there. So that's the water going from a liquid to a gas. And why does it cost us energy? Because those water molecules, if they're a liquid, are still touching each other. And we have to break those interactions between the water molecules apart in order to get gaseous water. Water where the molecules are not attached to each other, essentially. Oof. Photosynthesis. This one's an interesting one. So again, give it a quick think. Okay, so photosynthesis involves the sunlight being taken in by the leaves themselves, and the leaves then use that energy to take carbon dioxide and water and make it into sugar. So the fact that the leaf has to take energy in means that this is an endothermic change. And we see these all the time in nature, but we're much more often aware of the exothermic reactions because obviously they cause us a little bit of trouble. So let's think about a reaction itself. We've seen these reactions so far, so this idea of hydrogen and oxygen going together to make water, we've got sodium and chlorine reacting to make sodium chloride. All of these are reactions and they have a reactant in them, so that is the thing that is being changed. And the products are the outcomes of that change. So some of them involve just an electronic transition. So here, for instance, we've just got electrons moving around, and the same thing going on with the sodium and the chlorine as well. The sodium is giving up its electrons to the chlorine to make the sodium chloride. In the top reaction there, we have a complete change of partners in a covalent set of molecules. So the hydrogen is covalent, the oxygen is covalent, the water that's made is also a covalent compound. So why? Why do these things rearrange in the first place? Well, let's imagine that the substances themselves have a certain given energy, and that is the energy that's sort of retained in the bonds, in the vibrations or whatever of that molecule. In order for it to change, there has to be a good reason for it to change, and this has to do with strength of the bonds themselves. So if we have an exothermic reaction, what we would expect to see is that the products are lower down in energy than the original reactants. What I mean by that is the products are somehow more stable than the reactants themselves. Well, we know that hydrogen is an explosive gas, so we know that it is not quite as stable as something like helium or something like that. And oxygen is also quite reactive. It's involved in every explosion because it is providing the oxygen in order to do that reaction. What this really means, though, is that we've got stronger bonds in the product molecules or more stable ions or something like that. So if we went back to thinking about the copper and the zinc, for instance, swapping their electrons, and where we said that zinc is a more reactive metal, so it forces its electrons onto the copper. So a lower down line there means more stable bonds or ions or something like that. Now, the reaction of hydrogen and oxygen doesn't just go all on its own, so there we're likening this to the flames that we saw before. In fact, we have to provide a little bit of energy, which we call the activation energy. So if we were to plot what the energy of the molecules is as we go along during the reaction, and this would be called the reaction coordinate, just means how the reaction changes over time, then we would see that there is sort of a hump there where we're providing the energy, and then after that it gives out energy in some way. So the question is, why do we have to provide the energy in the first place? And we're describing that as the activation energy there. Well, atoms forming covalent bonds means that the atoms complete their octets, they complete their shell. And the whole point in completing your shell is to get to a stable electronic configuration. So breaking those bonds, because if you notice, we've got to rearrange the hydrogen molecule so that they're no longer attached just to each other, but now they're attached to the oxygen molecule as well. And the same thing for the oxygen molecule, separating into atoms so that those atoms can reattach. That must cost us energy because it goes from a stable configuration of at least completing its octet by sharing electrons to an unstable configuration which is separate atoms completely. And then overall there is some energy given out, which means that the new compound has stronger bonds inside it. And that energy, the difference between the starting material, the reactant, and the final thing that's made, the product, is energy that's lost to the surroundings in that process. It's given out. So like the fire we saw there, given out in the form of light and heat and maybe a bit of sound as well. This is well, that's a good question. Let's see. Would we say that this is an exothermic or an endothermic reaction? So which one is it? Let's look at what the reaction is overall doing. Now, if energy is being lost to the surroundings, then this must be an exothermic reaction. And that is because the new compounds are lower down than the original, or we haven't had to provide all of the energetic change there. So we haven't had to provide all the energy to make it change. And I'll show you what one of those looks like in just a second. But the fact that the arrow going from reactants to products is pointing downwards tells us that there's a negative change in energy. And by that, what we mean is energy given out to the surroundings. How about if it was going in? So now we're thinking back to our things like our photosynthesis. There, energy is taken in. That suggests that the reactants were somehow more stable than the products that are made. And in that case, we're thinking about things like carbon dioxide going to make a sugar. Well, we know that we can burn sugar and make carbon dioxide, and that process is an exothermic reaction in itself. And in case you don't know why you know that sugar is propellant in fireworks and things like that. So it's a really nice source of energy. In that process, the activation energy to break the bonds costs us a certain amount of energy, so we still got that upwards slope in the reaction pathway here. But then the energy that's given out is not as much as the activation energy that we originally put in. And that means overall energy has to be removed from the surroundings. And again, we're thinking about things like water evaporating. That's doing the same sort of thing. We're having energy being used from the surroundings to promote that water from a liquid form up to a gas form. And we know that water will spontaneously move from gas back to liquid at low temperatures. So again, this must be an endothermic reaction, i.e. the arrow between the reactants and the products is upwards. It's a positive change in energy that has had to be provided by us, essentially, or the system, or some external energetic source. So this one is an endothermic reaction. Now, again, that downwards arrow, so let's go back to exothermics for a second here. If we figured out exactly what the energy was that was being held within those bonds and what the new energy of the new products were, we can calculate something called the delta H. Remember the delta triangle shape? That means change in, and H in this case is enthalpy. I realise it's not a helpful letter, but that's what it is. So H is enthalpy. Here, the fact that the number is negative, as I mentioned, means that that's being given out to the surroundings. And there we go. Delta H is negative in exothermic systems. And what does that mean about endothermic systems? It must be positive. So again, if we had... These numbers are completely arbitrary. I've just made them up just to show the difference in delta H. We will only really see these arrows, the change in these arrows, when we do our measurements of that reaction, whatever it is. So with the fire, feeling the heat, what we're only really feeling is the difference in energy between the reactants and the products. We're not feeling like all the activation energy and all of the new energy being formed, given out. That's not technically true. Energy can't be formed. It's being converted from one form into another. So let's have a quick look at what's happening. In the exothermic reaction that we had before, so we're going back to this, a hydrogen atom and half a mole of oxygen atoms here. So we got a mole of hydrogen atoms, half a mole of oxygen atoms, goes to make 1 mole of water molecules. Now, the half a mole of oxygen atoms is a bit annoying, isn't it? So what we're going to do is double everything up so we don't have to deal with halves here. Now, as I mentioned, the atoms forming these bonds in the first place is a favourable thing to do because they complete their octets. If we're going to break those bonds, that's going to cost us energy. And that is why in both reaction coordinates that we've seen, we start off with a slope going upwards in the reaction pathway here, what the energy is as the reaction changes for those molecules. So there is some cost to breaking those bonds, and you'll find the costs of breaking those bonds in the notes for this section, but also on the data sheet that is provided in examinations on this course. So breaking bonds costs us a little bit of energy, and if we have a look at those data sheets, what we see is that breaking a mole of hydrogen bonds costs us 435 kilojoules. So it's 435 kilojoules per mole. Remember, when it's mole to the -1, that can also mean per mole. I've got 2 of those because if I go back to that equation, back there, we doubled it so that we wouldn't have this half a mole of oxygen in this equation. Okay, so then we look at oxygen. Now, let's just think ourselves. Do we expect this number for the breaking of the OO bond to be higher or lower than the breaking of hydrogen? Well, it's a longer bond. So, and the way that we know it's longer is we just look at the periodic table and we notice that oxygen is on the second row and hydrogen is on the first row, which means that the oxygen atoms are bigger than the hydrogen atoms, which are relatively small. That might say, oh, it's a weaker bond, but the oxygen molecule has a double bond in it. So perhaps those two factors are going to roughly equal out. I'm not entirely sure, so let's have a quick look at the number. I would expect that the number for the oxygen double bond is going to be significantly larger than the hydrogen one, but let's see. That's only my gut feeling spectrometer. Okay, 498. So it's kind of a little bit stronger, and that makes sense from the two factors that we just thought about. Now, how about the OH bond? Well, the OH bond is going to be a single bond, isn't it? Because it's the water molecules, oxygen only making two bonds. But they are going to be shorter than the OO double bond. Probably not quite as short as the HH double bond, but something like that. So if in this case we've paid all of that energy to make the change, then what we expect, given that this is an exothermic reaction, so let's just quickly look at the pathway again for a second. If this is an exothermic reaction, the bonds that are formed in the products must somehow be stronger than the total cost of all the bonds that we broke. So let's just quickly look at the total cost. We add all that up together and it's plus 1,368. So in this coordinate, that would be what this upwards arrow is then. That plus 1,368, and there that is. Okay, well let's have a quick look at the water molecules. So forming bonds must be a favourable thing to do. The separate oxygen and hydrogen atoms do not have complete outer shells of electrons, and so are not very stable. And in forming those new bonds, whoop, like that, we actually get energy given out because that goes from an unfavourable position to a favourable position, and that makes things better for the molecules themselves. Okay, so each OH bond then is 465 kilojoules per mole, so somewhere in between the oxygen and the hydrogen, and that kind of makes sense given that its length is somewhere in between the oxygen and the hydrogen. It is slightly stronger than I thought it was, and I bet that has something to do with electronegativity that we can talk about later on. So in the first set, we looked at the molecules that we broke apart, the hydrogen and the oxygen. We added together the bonds, so we're going to do exactly the same when we're thinking about energy that's being given out now. The first one was positive because that was energy being given into the system. Now that energy is being given out by the formation of bonds, we have a negative value. So we're taking that 465 kilojoules per mole, we're timesing that by 4 to give us a total of minus 1,860 kilojoules per mole. So let's just have a quick look at what that's going to be together then. So if we add those together, the change in enthalpy, we can think about this as basically drawing a graph where it goes plus 1368 and then minus 1860. And I personally would just always do it like this. Always write bond breaking as a positive value, bond making as a negative value, and then you just add those together. You don't have to take control of the signs because we're doing two processes. We're doing the process of breaking and the process of making. So when we do those together, we popping them in. Whoops, skipped through there. Okay, so we've added those values together and we end up with minus 492 kilojoules per mole. Now the thing is that we could think about that as minus 492 kilojoules per mole of oxygen burned. That would be absolutely fine. But if we were trying to talk about per mole of hydrogen burned, then we would have to say, okay, we'll divide that by 2 in order to give us that. Now, you could calculate this from where it was in the first place, so without doubling the reaction at all, and you just use half a mole instead of a whole mole of oxygen bonds. So if we look at that, then what we expect to do is basically get the same answer, just half as much this time. So again, minus 930. The cost of breaking these bonds is 684. We get out 930 kilojoules per mole. Overall, the enthalpy change then of this reaction is minus 246 kilojoules per mole. So again, half of what we had on the last slide there. Now, in general, the way that this works, if we're measuring this, so at the moment this is a theoretical value. It's based on the average OH bond, the average HH bond, the average OO double bond. But not all molecules are, as you would expect. So what we do is we define then this term as standard enthalpy. The standard enthalpy is given per mole of the compound or element, and it is calculated at the standard temperature and pressure of the Earth, which are given there. 298K is 25 degrees Celsius, 101,325 pascals, or 1 atmosphere, or 760 torr. All of those mean the same thing. If they're in solution, we just say it's a 1 molar solution, and again, this just keeps everything constant. So how do we actually do this in the real world then? If I actually wanted to go back to that explosion that we were looking at with the slow-mo guys and figure out how much energy is given out per mole of the fuel that we're using, then what I would do is I'd set up a calorimeter. So a calorimeter looks a little bit like this. So we have the reaction happening underneath a sort of cup of water, if you want. So let's say that we're burning some alcohols, for instance. We burn our alcohols in the spirit burner, and we try and capture all the energy in the water. Now, what you want to do is use something like a very, very conductive material, and copper is the most conductive material that is also reasonably cheap to buy. So we make the cup out of copper, and we put the flame underneath there, and we try and arrange the reaction such that as much of the energy from the flame, from the burning of the alcohol, or whatever the reaction that is happening underneath the calorimeter, goes into the cup itself. We have to use a known amount of water, and then we also have to have a thermometer in there, and that's because of the term calorie that we'll define in a second. But calorimetry itself is the study of the enthalpy change of the reaction. So when the substance is burned, it could also be other reactions. So you can reconfigure this system to be a tank of water where the reaction is happening inside in a cup, in a sealed cup in there. So that is if you don't have a flame coming off the reaction or something like that. So once we've got this set up, we need to figure out, well, how does one convert into the other? And you've probably heard the term a calorie. A calorie is the amount of energy it takes to heat up 1 gram of water, or 1 centimetre cubed of water. They are really, really approximate. They are very, very similar together. They're not approximately similar, they're very similar. So if 1 calorie is the amount of energy it takes to heat up 1 gram of water by 1 degree Celsius or 1 degree Kelvin, they're the same gaps in between them, then we can basically weigh the amount of water that we've put in our cup, and we can measure how many degrees it changes by. And by taking those 2 very simple measurements that you could take yourself probably at home now, we can figure out what the energetic change is, because the energetic change is going to be the mass of the water times the C. C is the specific heat capacity. That is basically saying 1 calorie in there. So we take the mass of the water, times it by the specific heat capacity, and then times it by the change in temperature. So if I've heated up, let's say, a litre of water, so that's 1,000 millilitres of water, or 1,000 grams of water, by 1 degree, then I must have provided it with 1,000 calories, and we call that a kilocalorie. And in fact, when you've got things like beautiful sweet popcorn here, the values given are in kilocalories on the whole. I don't know, you probably won't be able to see that, 1 sec. So they tend to be given in kilocalories, and they're also given in kilojoules up there, so it's quite hard to see. But the value given in kilocalories is to do with this very simple method, really, of calculating the energetic change within a reaction. Now, why is this useful? Well, let's say I'm inventing a new fuel or something like that. In that case, what I would want to know is how much fuel do I need to get a certain amount of energy out, so I can start to balance the weight of the fuel and how much I want versus how much power I'm going to get for it. Obviously, that doesn't, I mean, it matters a lot for our cars and things like that, but something like the shuttle or a rocket of any form, really, it needs not to carry too much weight, but it also needs to definitely have enough thrust. And so those calculations need to be very precise, which means that taking this measurement has to be very, very precise as well. So when they're calculating then on the back of the sweet wrappers here, what the energetic change is, this is essentially all they're doing, but they're trying to make it as accurate as possible by surrounding it in insulation, providing a stream of gas, making sure that gas touches all of the copper cup, making sure the copper cup has the maximum surface area and all of those things. But essentially, what it is going to be is that the change in energy is equal to the mass of water times the specific heat capacity times the change in temperature in there, and that will tell you the energy. This is a very easy calculation to do in a normal lab setting, and obviously the more precise your measurements, the better. Okay, so that's been a really quick canter through this topic. There will be some workshop materials for you to have a look at and have a go at calculating that energetic change with a given reaction, looking at all the bonds that you've got to break and make. But this was a very, very simplified version, and I hope that helps you. Thanks very much. I'll see you next time.